Good morning, everyone. I have taken this practical activity based topic called capacitor circuits in practical circuitry. As you already know, the capacitors are fundamental components in modern electrical and electronic system. Their ability to store and release electrical energy makes them highly useful in a wide variety of practical applications. In fact, there are some aspects we are going to talk about here. That is energy storage. That is actually energy storage is very important here because the capacitor temporarily store electrical energy, enabling power supplies to deliver quick bursts of energy. They're used in camera flashes, defibrillator, and the memory backup system. And there are some more aspects I will be talking about, like filtering and smoothing, then timing and waveform generation, like RC resistor capacitor circuits used in timer oscillators and a waveform generator. Then coupling and decoupling capacitor because it passes AC signal while blocking DC, and in amplifier coupling and stabilized voltage supply by absorbing voltage spikes and decoupling, you can understand. And the most importantly, the power factor correction in AC circuits. Power factor correction, what is that? In AC circuits, especially in industries, capacitor improve the power factor, reducing loss and improving energy efficiency. With this activity is designed with the help of FET Colorado, that is now, what is the utility of understanding voltage, charge, energy variation in capacitor circuits? Understanding how voltage V, here I have represented it by V, charge Q, and energy U stored in a capacitor that may vary with the physical parameters, which is very crucial for designing and optimizing a circuit. The behavior differs significantly in two conditions: with battery connected and with battery disconnected. I'll be talking about both of them in this virtual experiment. Here you need to first remember some of the aspects, like battery connected keeps V is equal to constant, the voltage is equal to constant. So here the capacitance how it is, it doesn't change with voltage, but charge Q is equal to CV you have to apply, and energy U, that also is half CV square. So if the voltage, energy increases, and its application is enhancing energy storage without altering circuit voltage. Whereas here when the battery is disconnected, the battery disconnected means Q is equal to constant, but V may change here. So V is equal to Q by C. So in that case, V is inversely proportional to C. Energy will be Q square by twice C. So U will be inversely proportional to C. And where does it find an use? The application is capacitive sensor and energy conservation. And in this virtual experiment, I will be largely talking about this. You will be going through it, and here this understanding of variations is vital for designing energy efficient compact circuits, engineering smart capacitive sensors, predictive behavior of the circuit during the switching, tuning or fault condition, exploring advanced technologies like touch screens, the MEMs, and the energy harvesting system. So let's come forward for a deep understanding of capacitor behavior with connected and disconnected battery conditions, allowing the engineers and the students to appreciate the interplay of electrostatics, circuit dynamics in real world electronics. So let us come forward to do this experiment and complete this. I'll be giving you a table there. Complete this table here. So let's come forward. This is a FAT Colorado based activity. This is E activity. So here we have taken capacitance as green color, plate charge as red color, and yellow as stored energy. You can see when the distance increases, the capacitance decreases, and here actually battery is connected. You can see it is upward and downward movement, but the 1.5 volt, the battery voltage remains constant. If the plate area increases, the capacitor increases, the plate charge decreases, and the energy also decreases. Now you can see when the battery remaining connected, and we are now increasing or decreasing the plate area. You can see the changes here. Now we'll be also checking the dielectric slab, but first increasing the distance. You can see the increasing the distance, what is happening. The capacitor is decreasing, but here now this area, the plate area has been increased, and we have taken out the dielectric slab. So the capacitance decreases, and there is no change in the plate charge because we have disconnected the battery here. And you can see the increase or decrease of stored energy, and we will be also seeing if we increase the dielectric constant. At present it is dielectric constant is 1.84, but it is increasing, and gradually when it is increasing, the capacitance is increasing with K or epsilon r value, and similarly with the battery connected also we will be having some. Here the dielectric constant is increasing or decreasing. You can see now there is a table here. This table you have to fill in. Just put an arrow. If it is upward, that means it is increasing. If it is downward, it is decreasing, and in case it is horizontal, it means it remains constant. So all the best. Please try this.